आज आपण सुरू करणार आहोत न्यू टॉपिक एनालिटिक फंक्शन. A function f of z of a complex variable z is said to be analytic at point z naught if f dash z exists at each point of z in the some neighborhood of z naught. So this is an example. Show that f of z is equal to modulus of z square is not analytic at any point z not equals to 0. So for that we have to show f dash z exists, that is the derivative exists at does not exist at any does not exist at point z not equals to 0. So for that, take the by definition of derivative limit z delta z tends to 0 f of z plus delta z minus f of z upon delta z. Okay, this is the definition of derivative. So limit z tends to 0, delta z tends to 0, f of z plus delta z can be written as modulus of z plus delta z square, because f of z is modulus of z square. F of z is modulus of z square, so minus modulus of z square. So this modulus of z square can be written as z plus delta z into conjugate of z plus delta z minus z into conjugate of z. So multiplying this, we get z into z bar plus z into delta z bar, delta z into z bar, and delta z into delta z bar minus delta z into z bar. So this z bar minus z bar gets cancelled. Here we get just z into delta z bar plus delta z into z bar upon delta z plus delta z bar. Okay, because here delta z cancel, there is only remains delta z bar. So at z is equal to 0, at that is at origin, the equation 1 reduces to uh, if z is equal to 0, it becomes, this terms becomes 0, this becomes 0. So only there is only one term delta z bar. So limit delta z tends to 0, delta z bar is nothing but 0. So f dash z is 0 at z is equal to 0. So f dash z exists only at origin, so is 0. So suppose that f dash z exit if z is not equal to 0. So along the path, any path, we get the same value of f of z. So consider the real axis, consider the path along real axis. So delta z is equal to delta x, so delta z bar is equal to delta x bar, so that is delta x. So putting these values here, we get uh, f dash z is nothing but limit delta z tends to 0, z into delta z bar plus delta z into z bar upon delta z into delta z bar, as by using equation 1. F dash z is nothing but this. So putting all these values, as delta z bar is delta x, z is equal to, so here we get it is, if we take the common as delta z, so we get here it is a z plus delta z bar into delta z upon delta z. So it becomes limit plus delta z tends to 0, delta z bar, so z into z plus z bar plus 0, because this limit is 0 as delta z not equals to 0. So f dash z is equal to z plus z bar for real axis. For imaginary axis, it becomes delta z is equal to I delta y. So by here we can put it is I delta y. So here we get it is z f dash z is equal to z bar minus z. So from along two different paths, we get two different limits. So the limit of given function, it does not exist at z not equals to 0. So f of z is not analytic on the complex plane except z is equal to 0. Okay, these are some remarks. A polynomial function in Z is analytic everywhere in the complex plane. If P of Z and Q of Z are polynomial functions of Z, then this quotient function P of Z upon Q of Z is also analytic everywhere in the complex plane, where this is provided that Q of Z is not equal to 0. Okay? So point of the domain of the definition F at which f of z is not analytic is called singular point of F in that domain. The necessary and sufficient condition for a complex function f of z is equal to axy plus ivxy, it to be analytic at point z is equal to x plus iy, is that it satisfies the Cauchy-Riemann equations. Simply it is called as CR equations, that are nothing but ux is equal to vy and uy is equal to minus vx. Ux is nothing but a partial derivative of u with respect to x, that is del by u by del by x is equal to del by v by del by y, and uy is nothing but del by u by del by y is equal to minus of del by v by del by x. So these are the necessary and sufficient conditions for analytic functions. So for the proof, so we have to consider the f dash of z. F dash of z is equal to limit delta z tends to 0 f of z plus delta z minus f of z upon delta z gives this equation number 1. Now RHS of equation 1 exists as its same along the path delta z is equal to 0. So for that, for now z is equal to x plus iy and delta z equal to delta x plus I delta y. Consider the following two cases. Along the real axis delta z tends to 0 along the real axis, then as along the real axis delta y tends to y is equal to 0, so delta y is equal to 0, so delta z is equal to delta x plus I delta y. Since delta y is equal to 0, delta z must be equal to delta of x, so delta z tends to 0 implies delta x tends to 0. So this limit becomes f dash z is equal to delta x because here delta z tends to 0 implies delta x, so limit becomes limit delta x tends to 0 f of z plus delta x minus f of z upon delta x. Here we can replace delta z by delta x. So here it can be written as z is nothing but complex number x plus iy plus delta x minus f of x plus iy upon delta x. So it becomes x plus delta x plus iy is x plus delta x is a real value, and y is a imaginary value, so minus f of xy. So so by putting these values in f uxy plus ivxy, so u x plus delta x y minus I into plus I into v into x plus delta x plus y minus uxy plus ivxy. So this real part is nothing but ux plus delta x y minus uxy. This is a real part, and imaginary part is plus I into v of x plus delta x y minus vx of v of xy upon delta x. Delta x is common for both. Okay, now taking the limit separate for this, take the limit separate for this and limit separate for this. So it becomes now its limit of value of this limit is nothing but d by u by d by x. This is the definition of partial derivative d by u by d by x, and this is the definition of partial derivative d by u by d by v by d by x. So if dash z is equal to d by u by d by x plus I d by v by d by x. So f dash z is, or it can be written as w by x can be ux. So partial derivative of u with respect to x plus I v x. Vx is nothing but partial derivative of v with respect to x. Gives this equation number 2. Similarly, case second, delta z tends to 0 along the imaginary axis, that is x is equal to 0. It becomes delta x is equal to 0. So delta z must be delta x plus I delta y. So delta x is 0 means delta z is equal to I delta y. Putting these values, we get f dash z is equal to delta y tends to 0 f of z plus I delta y minus f of z upon I delta y. So f of z, put the value of z is x plus iy. So here x is the only real part, I into y plus delta y is a imaginary part minus f of x plus iy upon I delta y. So putting the value of f of xy in terms of u plus iv, so u of x y plus delta y plus I into v of x y plus delta y minus u of xy plus I v of xy upon I delta y. So 1 upon I is nothing but minus of I. So putting these values of minus of I here, so we get here u x y plus delta y minus u x y upon I delta y plus I into v of x into y x comma y plus delta y minus vx upon I delta y. So 1 upon I is minus I, so it becomes um, here it becomes it's a minus of I ux comma y delta plus y plus delta y minus uxy upon delta y, and this is minus of I into I. So this is a plus limit delta y tends to 0 v of x comma y plus delta y minus vx upon y. So it becomes this is nothing but del by u by del by y into minus of I, and it is del by v by del by y. So it becomes minus I into del by u by del by y plus del by v by del by y, that is vy minus I u y. So equation, this gives equation number 3. Since f dash z exists, so limit of f dash z are equal. So equating the equation 2 and 3, we get ux plus ivx is equal to uvy plus iuy. So real part, comparing the real part is equal to real part. Yes, a real part ux is equal to vy. It's a real part is vy. So ux is equal to vy and vx is equal to minus ui. This is the imaginary parts. So equating real and imaginary parts, we get ux is equal to vy and vx is equal to minus vy is equal to minus vx. This proves the these are the CR equations, and this is known as Cauchy-Riemann equation. If the now show that this is the example of converse of above theorem, that is the show that the function defined by f of z is equal to root of modulus of xy when z not equals to 0, and f of z is equal to 0 is not analytic at z is equal to 0 even though CR equations are satisfied. So जर आपण वरती थिरम मध्ये बघितला, जर एखादं फंक्शन एनालिटिक असेल तर ते सीआर इक्वेशन सॅटिस्फाय करतं, पण जर एखादे सीआर इक्वेशन सॅटिस्फाय करत असेल तर ते एनालिटिक असेल असं नाही. दिस इज अ एक्झाम्पल provide for the converse. So f of z is equal to root of modulus of xy is equal to u plus iv. So this is a real part. So u is equal to root of modulus of xy and v is equal to 0. So ux is equal to 0. Ux of 0 0 is nothing but limit h tends to 0 u of h 0 minus u of 0 0 upon h. So limit h tends to 0 0 minus 0 upon h is equal to 0. So similarly uy of 0 0 is again 0. So what we get, the f dash of z, f dash of z is so CR equations are nothing but ux of 0 0 is equal to vy of 0 0, uy of 0 0 is equal to minus v of 0 0. CR equations are satisfied. But so what about the different derivative at z is equal to 0? So limit z tends to 0, f of z minus f of 0 upon z is equal to 0. So put the value of f of z. F of z is nothing but modulus of modulus of sorry under root of modulus of xy. So f of z is equal to if along the real axis y is equal to 0, so f of z upon z becomes under root of modulus of x into 0 because y is equal to 0 upon x. So 0 upon x is 0. So this limit becomes 0 along real axis. Now along the path y is equal to x, if you take the along the path y is equal to x, then limit z tends to 0, f of z upon z becomes limit x tends to 0 modulus of sorry under root of modulus of x into y, put the y is equal to x. So x into x, that is x square upon z is nothing but x plus iy. आपण y ची व्हॅल्यू टाकू शकतो, x कॉमन घेतला तर अंडर x इंटू 1 प्लस आय राहील. सो x एक्स कॅन्सल, हा x स्क्वेअर आणि त्याचा रूट स्क्वेअर रूट दॅट इज नथिंग बट x. सो x गेट्स कॅन्सल 1 upon 1 plus I. So limit becomes 1 upon 1 plus I. Along the real axis we get the limit 0. Along the path y is equal to x we get the limit 1 upon 1 plus I. So along two different path we get two different limits. So the limit of given function does not exist. This is a sufficient condition for f of z to be analytic. So f of z is equal to f of u, f of z is equal to u plus iv. Be if the four partial derivative ax uy vx vy exist and continuous at z is equal to x plus iy, then they satisfy CR equations u del by u by del by x is equal to del by v by del by y, comma del by u by del by y is equal to minus del by v by del by x at xy. Then f of z is analytic. This is the sufficient part, that is the converse. Here it requires the condition of continuity. We omit the proof of this theorem. Now solve example. So these are some solve example. Evaluate the limit z tends to 1 plus I z raised to 4 plus 4 into 1 plus I minus z upon z square minus 2 I z plus 2 I minus 2 z. So simply we have to find out the factors of z raised to 4 plus 4 in terms of this. So here z raised to we can add 4z square minus 4z square. So this is the perfect square of z square plus 2 bracket square minus 2z square, and it is a square minus b square. So in the first bracket a minus b, in the second bracket a plus b. So again find out the roots of this is nothing but 1 plus or minus I. So roots of this is z raised to 4 plus 4 is nothing but z square plus 2z plus 2 alpha z minus alpha z plus beta. Sorry, z minus beta, alpha is equal to 1 plus I, beta is equal to 1 minus I. So putting these all values, so and solving we get uh, solving we get this z minus alpha and z minus alpha. So these two common factors gets cancels and we get 8 plus 8I. This is the answer. Now these are some again examples which can be solved easily. Yeah, this is for example for if f of z and f of conjugate of f of z are analytic function of z, show that f of z is a constant function. So f of z is equal to u plus iv is an analytic function. So use it satisfies the CR equation that is ux is equal to vy and uy is equal to minus vx. Similarly, conjugate of f of z is equal to u minus iv is again analytic, so it also satisfies ux is equal to minus vy and uy is equal to minus of minus vx, that is vx. So adding these two 1 and 2 we get 2ux is equal to 0 and 2uy is equal to 0, that is ux is equal to 0, uy is equal to 0. So if dash z is equal to ux plus ivx, there's a ux minus iuy is equal to 0 plus 0 minus I 0, that is 0, and a derivative of function is 0 means the given function is a constant function, because the derivative of constant function is 0 only. Okay. Next example, if f of z is analytic function with constant modulus, then f of z is constant. This is given f of z is equal to u plus iv with a constant modulus, that is modulus of f of z is constant, that is under root of u square plus v square is equal to k. K is a constant. If we take the square from both sides, so u square plus v square is equal to k square. So differentiating equation 1, we get 2u, since u is a function of u, x and y. So this is a 2u ux 2v vx is equal to 0. So we can take 2 as a common and divided by divided throughout divided, so we get u into ux is equal to plus v into vx is equal to 0. Similarly, differentiating equation 1 with respect to y, we get u into uy plus v into vy is equal to 0. Since f of z is equal to u plus iv is an analytic function, uv satisfies the CR equation, that is ux is equal to vy and uy is equal to minus vx. So using CR equations, so put the values of CR equation in equation 3. So we get u into v minus vx plus v into vx is equal to 0. So solving 2 and 3, we get ux is equal to 0, vx is equal to 0. So f dash z is equal to ux plus ivx, but both the value ux is 0, vx is 0. So f dash z is equal to 0. So we get f dash z is a constant function. Now show that daba square by daba x square plus daba square by daba y square is equal to 4 daba square upon daba z bar. So z is equal to x plus iy and z bar is equal to x minus iy. So x is equal to 1 half of z by z, 1 half of z plus z bar, and y is equal to 1 upon 2y z minus z bar. So daba of z, daba daba by daba z is equal to daba by daba x into daba x by daba y, and deba by deba y into deba y by deba z. So we can find out deba x by deba z. याचा पार्शियल डेरिव्हेटिव्ह विथ रिस्पेक्ट टू झेड काय येईल? इट्स अ वन हाफ. पार्शियल डेरिव्हेटिव्ह घ्यायचा विथ रिस्पेक्ट टू झेड बिकॉज दिस इज कॉन्स्टंट. सो याचा डेरिव्हेटिव्ह विथ रिस्पेक्ट टू इज वन हाफ. सो याचा डेरिव्हेटिव्ह विथ रिस्पेक्ट टू झेड इज again 1 upon 2y. So putting these values 1 half and 1 upon 2y again. So 1 half deba by deba x plus 1 upon 2y I upon I. So 1 upon I is nothing but minus of I. So minus of I upon 2 deba by deba y. So this is deba deba z is nothing but 1 half of in the bracket deba by deba x minus I into deba by deba y. Similarly, we can obtain deba by deba z bar is nothing but 1 half of deba by deba x plus I into deba by deba y. So comparing these two, or this we can take the deba square by deba z bar, that is the deba z of deba by deba z bar. So here we can calculate, we already calculated the deba by deba z and deba by deba z bar. So putting these values, 1 half of deba by deba x plus sorry minus I into deba by deba y plus into 1 half deba by deba x plus I into deba by deba y. So taking multiplication, we get this is 1 half into 1 half 1 by 4 deba by deba x, and this both are equal. So this is nothing but it's a square of this deba square by deba x square plus deba square by deba y square. So 4 of deba square by deba z bar is equal to deba square upon deba x square plus deba square upon deba y square. These are some exercise on these chapters. In the next lecture, we have to see the next new topic, construction of analytic function.